So this morning I'm going to be talking to you about factor graphs, belief propagation, and density evolution. Really, this is going to be a almost completely tutorial talk. I guess the very end, I wouldn't only be a tutorial for very few people. Most people to be new information. In particular, my goal is to try and introduce the topics that are going to be used by a bunch of the talks after this. So I know in this case, because of people I invited, that a lot of these concepts are going to be used in multiple talks after this, and I'm going to try and point out where those concepts are going to be used. Now, I don't know really for the people more in the theoretical CS community how much factor graphs are used and whether this is completely known stuff for them or if it's somewhat new. So maybe we'll find out as we go. So here's the outline. Just a quick introduction where I tell you the names of the words in the title or the meaning of the words in the title. And after that, I'm going to give a little introduction to factor graphs. And then talk about some applications. And then in particular, I'm going to talk a fair bit about spatially coupled factor graphs. And these are essentially factor graphs that have a nice property under belief propagation. So that when you do low complexity decoding, the performance is very good. We'll kind of talk a little bit about why. And we'll talk about some properties of this. In the end, I'm going to talk about kind of the mathematical property that makes this true, which is called threshold saturation. All right, so definitions. So what is a factor graph? Now, of course, we're going to define it mathematically eventually. But for the purpose of this part of the talk, we want to say it's a compact description of a joint distribution for random variables. And it gives a natural setup for inference problems. So in general, in many inference problems, you can say I have some random variables and I just know something about some pairwise marginals or something like this, and I'm going to use this to define the whole distribution. And that's what factor graphs let you do. Once you have a factor graph for a problem, you can talk about doing some kind of low complexity inference on that factor graph. That's called belief propagation. And so this is a message passing algorithm for inference. So in general, what we want is we want a simple kind of iterative update that allows us to do inference for the model we've defined by a factor graph. So probability estimates in belief propagation are passed along the edges of the graph. So I give you a graph. One side of the graph is going to be variable nodes. The other side of the graph is going to be factors, which kind of enforce knowledge about local small joint distributions, either pairwise marginals or triples of these kinds. And then on that graph, when I want to do inference, I'm going to pass messages along the edges, which correspond to probability distributions for my current estimate of variables. The reason that belief propagation, I think, receives a lot of attention is because it provides an exact inference algorithm if your factor graph is a tree. But that's not really why people use it. The reason that people use it is because it provides a pretty good estimate even if your factor graph is not a tree. Because for the most part, interesting problems don't have factor graphs which are trees. I mean, it's not entirely true, but... Now finally, density evolution. This is the analysis method for when you're doing belief propagation inference. So you have some model you specified by a factor graph. You decided I want to run belief propagation to try and infer the values of the variables in that model. And you want to know how well is that going to work. So in the large system limit, if you can picture a very large factor graph that has some kind of regular structure in the limit, you could ask the question of how well will belief propagation inference work, and density evolution allows you to answer that question. And the way it does it is by tracking the distribution of the messages. So on the belief propagation, in the belief propagation algorithm, where those messages are being passed around, if you knew roughly the empirical distribution of all the different kinds of messages in the graph, you'd have some idea how well it's working. So, and in some cases, this allows a rigorous analysis in terms of proofs. Often in that case, you have to have a very regular factor graph. It's chosen randomly, and in the large limit, the neighborhoods of nodes become trees, and then you can use essentially the idea that BP works well on trees. All right, so what are the applications that we're going to talk about? So error correcting codes is the application that I'm most familiar with. This is what really brought me to this topic, working on inference and graphical models. So in this case, we have a random code defined by a random factor graph. We're going to do low complexity decoding via belief propagation. And then we're going to analyze belief propagation using density evolution. Now, just to be clear, the setting that we're usually working in here is the standard one of error correcting codes, where you take a code word, you transmit it over a noisy channel, you get some observations of that code word, and you try and infer the original code word. So that's the inference problem we're solving with belief propagation. And then some notes here for myself. So of the talks coming after me who are going to talk about things using this, so we have Andrianova, Urbanki, Poincaré, and Macri. I'm leaving one off. And Sid. And Sid's going to talk about, so according to their abstracts, they're all going to use some elements of this in their talk, and belief propagation like this. Another topic that can be put in this framework of factor graphs is Boolean satisfiability. So in Boolean satisfiability, you're going to take a random, well, in general, you'd like to be able to solve a general SAT problem, but if you're working with factor graphs, you can pretty much only make arguments about a random instance of K-SAT, which is defined by a factor graph. And in this case, there's a non-rigorous analysis based on the cavity method. And for K-SAT and large K, this analysis was recently proved to be correct, so it gives the right answers. For small k, it's still undecided. But so one of the nice things about factor graphs that allows you to view this in kind of a unified framework and understand how these things work. There's also a non-rigorous decoding algorithm associated with that. I guess there's a couple of them. There's belief propagation guided decimation. It's the one I'm going to talk about a little bit. And that's going to give us some idea of how we might solve a K-SAT problem using low complexity methods. In that case, we don't quite have an analysis of it. There's some gap that opens up. So here we have belief propagation, and we can analyze belief propagation using density evolution. And for the K-SAT problem, we have what's called belief propagation guided decimation. And we have an analysis technique, but they're not for the same thing. So you can't actually say you can't make rigorous statements from that analysis technique. But the statistical physicist will tell you, of course, it's giving the right answer, and you can see why if you think about it, but you can't write down a proof for it. Finally, compressed sensing. Galen Reeves is going to talk about that tomorrow? Today? Perfect. All right. So in that case, we're going to have a random measurement matrix defined again by a random factor graph. In these previous cases, the factor graphs I was always going to consider would always be sparse. That's going to give you nice properties. In compressed sensing, people were often assuming this factor graph is dense. And so once again, you're going to have low complexity reconstruction versus via message passing. In this case, the message passing algorithm often goes by the name of approximate message passing, or AMP. And there's something like a density evolution, which is called state evolution for this algorithm. And so the same idea kind of appears again. And Donahoe, Javanmard, and Montanari proved that when you do spatial coupling with that particular model, this achieves the information theoretical optimal limits of compressed sensing. Now, there's a lot of slightly different ways to define that, so later we'll talk about what that actually means. All right, and then also speaking in the next few days, will be people using some of these techniques, but maybe slightly different applications, not shown here. So Poincaré, Macri, my brain's early in the morning for me. Who else do we have? Sewong, which I haven't seen yet. O is going to be using these methods, and also Fontobel. Yes, Pascal. Thank you. All right. So everybody's going to be, not everybody, a lot of the speakers coming after this are going to be using these methods, so we thought we'd give an introduction to them. All right, a little bit more about factor graphs. All right, so a factor graph, more specifically than previously, provides a graphical representation of the local dependence structure for a set of random variables. So what does that mean? I'm going to have n variables, x1 through xn, and m factors, f1 through fm. And I'm going to use this to define a function which factors into a product, and use that function to define a distribution. So in particular, let's think of a small case where you have 4 random variables. And we have some y arbitrary observation, which is conditional given those observations. So we say that we're jointly distributed. I'm going to write some probability of distribution over those 4 random variables to be the probability of this given some y. And I'm just going to say it's proportional to this function f. So whenever I have a non-negative function and I want to turn it into a probability distribution, I can just normalize it. This works. And so if we assume here f is non-negative, but I'm also going to assume it factors into some smaller form. So in this case, it's going to factor into 3 terms, where f1 only depends on x1, x2, f2 only depends on x2, x3, and so on. So what this defines in this case is a Markov chain. So given some observation y, which is going to have, there's going to be an implicit dependence at all the factor functions for that particular y. I'm going to have a distribution over my random variables x1 through x4. And that distribution is basically going to describe a Markov chain. So how do we go from the graph to the functions? So in this case, what we see is we have function 1, which depends only on variables x1 and x2. So we take our variables x1 and x2, and function 1 is a function node which is connected by edges to those, indicating that x1 and x2 are both in function 1. Likewise, function 3 has edges to x3 and x4 because x3 and x4, or function 3 only depends on x3 and x4. So one of the nice properties of factor graphs is that even without knowing the functions, it represents some kind of conditional independent structure of your random variables. So what does that mean? So if we say we have 3 subsets or disjoint subsets of our variable nodes in the factor graph, we're going to say that the set S separates the sets A from B if there is no path in my graph from A to B that doesn't pass through a variable node S. And so these are subsets of my variable nodes. I'm going to look at paths through my graph. So if I go back, I can see, for example, that x3 separates x1 and x2 from x4 because there's every path from x1 to x4 has to pass through x3. So if this occurs, then what we have is we have that the subset of random variables x sub a is conditionally independent with the subset of random variables xb given x sub s. And so what does that mean in terms of these probability functions? So we're saying if we looked at some probability function of the realizations xa and xb given xs, then it would factor in this form. So in particular, in this Markov chain example, is exactly what I said. I'm going to take A to be x1, x2, B to be x4, and S to be x3. And so if I fix the boundary, so that means all the variables in this separating set S, I'm going to assign them values. I'm no longer going to think of them as random, but give them fixed values. What I'm left with is a function. In the factor graph, what I can do is I can absorb the effect of that S into these factor nodes. So they gain a prime, so the factor nodes become slightly different. And I've separated the factor graph into 2 components. And so groups of variable nodes in different components of a factor graph are independent. So that's the statement, which I will talk about in a second. And therefore, XA and XB are conditionally independent given S because the set XA lies in is defined by this part of the factor graph, and the set XB is defined by this part of the factor graph. So let's think about this. Yeah, so I think I will talk about this. So what do I mean by this? So what I'm saying is that if I have a function f of x a xb, and it's equal to f1 xa times f2 xb, then the probability distribution that's defined here, right? So how am I going to get a probability distribution? I'm just going to normalize. So I can say probability x equal to xa x. So this is just going to be gotten from here by normalization. So if I have this distribution here, so essentially what I'm saying, I write often this probability xa equals xa xb equals xb is proportional to f1 xa xb. So when I say it's proportional like this, I'm really just saying all I have to do is normalize it. What we can see is that we can push this sum forward and do these two sums separately. So this is just going to be f1 of xa divided by sum xa f1 xa times and that each one of these then is probability xa equals xa and probability. So whenever you can factor your function into two sets of variables which are disjoint. So the key here is that a and b are disjoint, so there's no variable in which they both depend on, and that's why I can push this sum forward and do these two sums separately. All right, so in some sense, this is the fundamental property that we use in factor graphs to understand how things work. All right, so now how do we do inference on factor graphs? So basically, the key operation that we'll use most often is marginalization. And so what that means is marginalizing out all variables except for one. So in particular, if I ask you what the probability of x1 is given to some equal to some little x1 given my observation y, I'm just going to say it's proportional to this function where I sum out all the variables except for x1. Now, in that case, if I wanted to make the maximum a posteriori decision on that variable, I could just take the argmax of that. There's a constant I'm leaving out, but it doesn't matter for the maximization, so I can get this. Now the question is, how much complexity does it take to do this sum? And so marginalization is efficient for tree-structured factor graphs, as we'll see shortly. But for this Markov chain example, which is a tree, we want to understand to some idea of how many operations are taken. So to compute this sum for every value, the way to think about this is I'm going to sum over x2, x3, x4 for every value of x1. If the cardinality of my alphabet, so I'm going to assume that all my x's are taking values in this calligraphy x alphabet. Basically, I have to do x cubed terms to sum for each x1, and there's that many x1. So I basically have order my cardinality to the power 4. Yes?
Sorry, there's just a question about like the terminology on the last slide. But now
okay.
Yeah, so these xi's are random variables?
So the capital Xi's are intended to mean random variables. Yeah, and then lower cases are like things I plug into my distribution function, but.
Okay, so those are almost the domain. Like the random variables take values amongst those.
Yeah.
Okay, and then so what again are these? What is F?
What is F?
Like F12.
So these are my factors. So this is the problem. So it's kind of like when you're given a problem like this, you're given the factor graph. And so what does it mean to be given the factor graph? So you're told the alphabet, right? The calligraphy x. You're told how many functions it factors into and what variables are, and you're told those functions. So it'd be like I'd say, I'm going to give you 3 functions, f1, f2, f3. They depend on these variables. And I'm going to define these functions by a table, right? Just for all possible values, I can define this function by listing its values in a table. And then I've given you the factor graph. I've given you the model.
And just notation, so if one of those f's, like if f1 had been a function of 3 variables, x1, x2, x3.
Yeah, so the indices are different. So in the sense that like, the fact that f2 has x2 in it is just chance here. We'll see another example. The index of the function is unrelated to the index of the variable, if that is your question. In this case, it's because it's a Markov chain, it's simple. The next example we'll see, I'm just going to order my functions in some arbitrary order.
Okay, so also aside from that, if it had 3 arguments,
Exactly. So we'll see an example shortly with a more complicated factor graph. Well, yeah, maybe I'll jump ahead to this picture to this picture. So maybe this is a more general case. So in this case, the function that I'm factoring is shown at the bottom, except for this sum. If you get the sum out, so it says f1 depends on x1, x2, and x3, and so there's f1, and it's connected to x1, x2, and x3. F3 depends on x4, so it's only connected to x4. F4 is connected to x4 and x5, and F2 is x1, x4, x6. And that would be something I'd give you when I set up the problem. All right, so let's see how we're going to use that. All right, so one of the things we're going to get from factorization is we're going to get lower complexity marginalization, and that's one thing we want. And so here's my example where f factors into a more general setting. As we saw in a slide later, it's going to be a tree still, so that's going to be useful. But if we were to set up this, now we have 6 random variables. So f is this function that factors in this form. And if we wanted to do this whole sum, now it would be the cardinality to the power 6. So you see, as you have more and more random variables, your cardinality is going to be growing exponentially if you have no structure. But if you have structure where each function only depends on a small number of variables, the cardinality may not grow at all, or may grow very slowly. All right, so one way to see how factor graphs work is just look at this as a problem of pushing sums forward. So I think this is a good way to think about it at a first cut. So you want to compute this sum. You have this function here, and you want to sum over x2 through x6, make them disappear. So what are you going to do? Well, you want to find some function where there's only one variable in there and nothing else depends on it. So in this case, we can look, x6 only appears in f2. So we could push that sum to the end. So we could essentially say, let's sum over x6 and f2 way out here. Why is that good? Because once I compute this sum, here the cost of computing this sum is really only equal to the degree roughly. So for each value of x1 and x4, I have to sum over all the values of x6. So it's basically the cardinality of my alphabet cubed. And now I can continue. So in this particular example, it's set up so we can just work our way backwards. We'll notice now x5 only appears in x4. So we can do that sum separately as well. So we can push this sum forward, and just inside here, we're going to sum out x5. And this is going to cost me my cardinality of my alphabet squared, because for each value of x4, to sum over all the x5. And I can continue. And so now, in this case, the next variable I'm going to sum over is x4. Now these both depend on x4, so I have to take their product, and then I can sum over x4, along with the one function which depends only on x4. And working my way back, I finally can sum over x3. Now in this case, none of these depend on x3, so that becomes a constant, and I'm really just summing out this function over x3. And finally, I sum over x2, and I'm left with what I wanted, this function which only depends on x1, which is my marginal for x1. Now, so we said if we did this naive, it was going to cost us cardinality of our alphabet to the 6th power. In this case, you can work it out, and depending on how you count things, it's roughly going to cost us the cardinality of the alphabet cubed. The right way to think about it is whatever the maximum degree of these factors are is usually the right answer in terms of the order. All right. Now, when I gave you this function, though, it may not have been obvious what order to do the sum in, right? So I knew the order I made the function. It's an example. But if I had drawn the graph, I claim that it's an obvious what order to do the sum in. So you don't need to have any special knowledge here. What you're really going to do is you're just going to look for leaf nodes. Any leaf node can be summed out and without causing any trouble. So in this case, I have my choice. I could do x2, x3, x6, x5. In particular, I'm going to use the same order as I just did, but I'm going to show it in the graphical way. So when I sum over x6, what happens? So we have this same product. We're summing over x6. Well, the way I think of it as an appealing thing is x6 vanishes, and I absorb its effect into some f2 prime. So I get some new factor function which doesn't depend on x6. It only depends on x1 and x4. And as I continue that, I can do the same thing. I can sum over x5, and x4 will become some new prime factor function, and so on. So here I'm going to sum over x4. F2 will get a second prime. And so what I'm doing is I'm peeling my graph down till I just have x1 and 2 factor nodes here. And so now that's my marginal. So if I would like to marginalize out when I have a tree structured model, it's a very simple procedure to just find any leaf, sum over it, and so on. This is going to give us the low complexity approach to marginalization. All right, so now let's talk about using factor graphs to solve constraint satisfaction problems. Now, constraint satisfaction problems have a special form for their functions. They're essentially 0-1 functions. So that's why I call these 0-1 factors. So I'm going to say a non-negative function defines this distribution, just like before. The probability is given over the x's. I'm going to have 1 on z, where z is called the partition function. It's just the sum, my normalization constant, times the product of all my factors. Now in this case I have a little more general setting in the sense that I'm going to think of my factors as being indexed by the letter lowercase a, and that each factor a only depends on its neighbors in the factor graph. So this boundary of a, if you think of it as a graph, in the graph the boundary of the factor node a is just the variable nodes which attach to it, its neighbor, and that gives me this subvector. So for a constraint satisfaction problem, all the factors are going to take on the value 0, 1. They're just going to say, do I satisfy the constraint or not? So when I take this product, if I wanted to know, does there exist something that satisfies this thing, I just have to say, is there a pattern where none of the factors evaluate to 0? That would be the question. And we can think about the set of valid configurations as all the configurations in our Cartesian product of our alphabet, where the function takes the value 1. And then when we do the sum now, here we see z, if we just, all the functions are either 0 or 1 and we sum over those, z is just going to be equal to the number of valid configurations. And if we look at this again another way, we see that actually this distribution is just uniform over the set of valid distributions because it's normalized by the number, and this is just an indicator function for the valid distributions. All right, so let's talk about some applications of factor graphs now that we have this kind of viewpoint. So a factor graph for the masses, Sudoku, the best example if you're trying to teach this to undergraduates, or really anybody who hasn't seen it before, because most people have played Sudoku at least once. So what does this mean? So now I have this grid, which is 9 by 9, and it's going to take values in the integers 1 through 9. And I know it's got some set of local constraints. In particular, it has a constraint that every row is a permutation of the letters 1 through 9. Every column is the permutation of the letters 1 through 9. And every block is a permutation, contains a permutation of the letters 1 through 9. If what I can do is I can then introduce a variable node indexed here, so x11 being this variable node for this corner, and I can write down the factorization of this function. So I can say I want f of x to be 1 if I have a valid Sudoku, and I want it to be 0 otherwise. And so what we're going to do is we're just going to have a product of the factors. So this is going to enforce all the row constraints. So I say, xi star implies here just the function of the ith row. This is going to enforce all the column constraints. X star j is going to be the jth column. And then here I'm going to have functions which just depend on the block. So I have 9 blocks as well. Now in general, I don't want just an indicator function of valid Sudokus, because then I can never solve it. So in this particular constraint satisfaction problem, I'm also given some hints. So I have here the product of the indicator that I have to choose x's which match some set of observations. So I have to think of all the Sudokus which have a 2 in this position, a 5 here, a 1, and so on. And actually the definition of a Sudoku includes the fact that it has a unique solution. So clearly we could write patterns of numbers up here where there are multiple solutions, but the idea of a Sudoku is that's not a Sudoku because it's not really a solvable puzzle. So now what can we do? So for myself, who doesn't solve Sudoku all that often, I pretty much follow the algorithm, the naive algorithm that you get from factor graphs. And I assume that anybody the first time they solve a Sudoku essentially follows this algorithm as well. So let's see what this algorithm is and talk about it for a second. So first, let's just say consider any constraint satisfaction with observed entries. So we see that f of x can be written as a product of indicator functions. And some factors are going to force me to pick a valid thing. So I want it to actually be a pattern where all the permutations line up. And the others force it to be compatible with some observations. And so when you sum over all the x's, this partition function is now going to calculate the number of valid compatible sequences for my particular problem. Now there's a low complexity peeling solution to these, especially this is really specifically for Sudoku here. And so what we're going to do is we're going to try and set the elements one at a time. At each step, we're going to look for some variable node and some value such that for the currently set variables, the factor is 0, it's unsatisfied for every other setting of that variable. Since I know there's a unique solution, I know this has to be the correct part of the unique solution. And so let's solve a simple Sudoku using this method. Okay, so instead of doing a 9 by 9, we will make life easier working on the board and do a 4 by 4 Sudoku. So in this case, I have just the numbers 1 through 4. I have 4 blocks. Everything is now 2 instead of 3 or 4 instead of 9. And so what I want to have is I want to have 1, 2. All right, so Sudokus of size 4 are fairly easy, so we don't need that much information to get started. All right, so assuming I did this right. Yes. There we go. So if we look at this position here as one of our variable nodes, we have to say we have 3 local constraints. So the local constraint here, right, is going to tell me this guy has to be 3 or 4, right? Or it's going to tell me that if I choose it to be 1 or 2, that factor is going to evaluate to 0. And if I look at this constraint here, if I choose it to be 4, then this factor will evaluate to 0. And so there's only one valid choice for that. So this isn't when the peeling is going to work. It's going to say we have to pick this guy to be 3 because otherwise one of our local factors is 0. Now, if you solve Sudokus maybe and you're good at them, it's not true that every Sudoku can be solved from these simple rules. So this is a very simple peeling algorithm that's not going to work in every case, but in this example it will. And now, of course, we can use a factor for just the row. Once we have any 3, we automatically know what the 4th one is from that one factor. Okay? Now, what can we determine now? Let's think about this. I think I got this one. All right, so I know if I look at this one, right, what values can I choose it to be? So I have to choose it to be 1 or 2 from here, but I guess it's in particular this one. I have to choose these to be 1 and 2, but if I choose it to 1, I'll have a 0 here. That's going to tell me that this one has to be a 2, and therefore this is a 1, and so on. So at each stage, I can do this peeling solution if I can find a variable node or a position in this matrix where all the values except for 1 cause it to be unsatisfied. So there can really only be 1, and I can peel this down. All right, so is that clear? Who has not solved the Sudoku? Who have I just taught Sudoku to? Good. So the goal of this puzzle is actually to give you the right idea with something you do know. All right. So now how about Boolean satisfiability? So this is another case where we have, we can do similar things. Now, in this case, a SAT problem can be thought of as clauses, which are the ors of variables and their complements, the nots, anded together. So this I would read as not x1 or not x3 or x7, all anded with x1 or not x2, etc. So in the factor graph, each clause can be enforced by some function. So the first clause, I can take a function which evaluates to 1 only if this clause is satisfied and 0 otherwise, and so on. So if I wanted to sample from the valid set of satisfying assignments, I can use this simple algorithm. So what I'm going to do is I'm going to marginalize down to some variable and then sample that variable and continue. And in particular, I'm going to take some ordering of my variables. So in this case, I'm just going to take I going from 1 to n. And I'm going to think of fixing all the variables j less than I. So each time I'm going to fix a variable and just work my way forward. And so what I'll do is I'll compute this marginal, which is a normalized version of the sum. I'm going to sum over all the future x's of fx. And that's going to kind of give me something like the probability that xi is equal to xi given these past values when I think about the distribution defined by my function. And then I'll sample xi and fix it and repeat. So this is always guaranteed. This is just the factorization of probability, always guaranteed to find a satisfying assignment. But that's not really possible because there's not always a satisfying assignment. So what goes wrong if there's not a satisfying assignment? Where does this algorithm break down if my model is not satisfiable? Yeah, the very first step, when I sum and I try and find the normalization constant to pick the first variable, it's 0. So there is this other thing about factor graphs. There's always an implicit thing that my sum is positive, or else I can really do nothing. Now, the good side of this is I would detect that it was unsatisfied right away. The bad side is that the very first step requires exponential complexity. So this is not particularly a good algorithm, unless I happen to have a tree, and then maybe I can do this more efficiently. But what if we were to give you some other algorithm that allowed you to approximate marginals? So I'm going to say now I'm not going to do the full sum, but I'm going to have some low complexity way to approximate that marginal. Then I can use the same idea, right? I can approximate the marginal for x1. I can sample x1. I can approximate the marginal for x2, given x1 and sample, and so on. And this is not exactly, but this is very similar to the idea of BP-guided decimation as a way to solve SAT. So we would use belief propagation, which we'll hear more about shortly, to guide our choices to decimate or choose variables in the SAT problem. Now, I think Nicholas is going to talk a little bit about SAT. Your talk, are you still talking a little bit about SAT? Vaguely. So, all right. So maybe this is all we'll hear about SAT. But I'll mention later, there are some nice techniques from factor graphs that have been applied to SAT. So. All right, so what's another application? Check the time. Yeah. Point-to-point communication. So in this case, our channel model is the following. We have a transition probability py given x for some x in our input alphabet and some y in our output alphabet. What we're going to do is we're going to take a subset of the sequences of length n on our alphabet and call that a code book. And we're going to pick a code word from our code book and transmit it across this noisy channel. And so the Shannon capacity of this is a code rate, which is 1 on n log 2 of the size of our code book. And as n goes to infinity, reliable transmission is possible really if and only if the rate is less than c. And so this c is the Shannon capacity, and it's defined as the maximum over all input distributions of the mutual information. So I'm not going to dig into that so people know this. But one particular example is very simple, and that's where we have this thing called the binary erasure channel. And for the binary erasure channel, bits are either sent perfectly, so with probability 1 minus epsilon, when you transmit a bit, you receive exactly that value. And with probability epsilon, they're erased and you receive a question mark or a star, some symbol to tell you that it's been erased. In this case, the capacity is 1 minus epsilon, or just a fraction of unerased bits. And so the way you can see this, that roughly 1 information bit for the binary case, roughly 1 information bit is transmitted for each unerased position. And it's clearly the best you can do, because these erasure symbols give you no information. So you just, every time you receive a symbol, it's going to give you some information. Now, in terms of factor graphs, low density parity check codes, which actually were defined in the 60s, they predate the definition of factor graphs and belief propagation, are really the prototypical model that we'll think about. And in this case, the variable nodes are going to represent code bits, and the parity checks are going to, function nodes are going to be parity checks. And the way we're going to do is we're going to generate a large random factor graph by just fixing the degrees of our variable nodes on each side. So in this case, I'm going to choose degree 3 variable nodes and degree 4 check nodes. And I'm going to use a random permutation here to map between them, to just give myself a random graph. That's going to define some constraint. And now, if I choose these parity checks to actually be 1, or these functions to be 1 if there's an even number of 1s attached to them, and 0 otherwise, this is going to define a linear code. So my code words are exactly going to be the set where if I hit x times h transpose and I get the all 0 vector, that's going to be a code word in the code book. So more particular, so I can think of this factor graph as the bi-adjacency matrix of this bipartite graph. And the configurations, let's see. So the factors are really just indicators of whether or not the mod 2 sum of adjacent variables is 0. And so what I can think of my function here for these is the product of all my constraints for each one of these checks. I also have observations. So I'm also having here this product of the probabilities of y given xi. Roughly speaking, this distribution, or if I normalize this function, it's going to give me the joint probability of a random code word and the observations. So if we take this function and normalize it, and we fix, say, an observation, what it's going to give me is this joint probability over all the code words for a fixed observation. All right. Now, if I can do inference in this case, I can do decoding. Because what I want to do is I want to say, given this received sequence, what's the most likely value for the bit 1? That's simply the marginalization problem. Now, belief propagation is how most of these algorithms work in practice. So belief propagation, going back to our model, is instead of peeling off these variables one at a time, what I'm going to do is I'm going to define an iterative message passing algorithm that gets the right answer after some number of iterations. And so what I've labeled here is I've labeled these mu's. So I can think of the variable to factor message. So each variable is going to send a message, I to A, which depends on this. We can think of this as a distribution over alphabet. So we can say that this variable is sending to this factor the distribution of what it thinks that the variable is. So if after some amount of information has been accumulated, I think the probability that this value takes is 1 is 0.2, and the probability it takes is 0 is 0.8, then I can pass this distribution to this check. What this check is going to do is a local update. Everybody gives me local information. They say, oh, I think it's this, I think it's that. But the factor node also has some additional information. It knows that the sum of all its neighbors mod 2 are 0. And using that knowledge, it's going to pass a message back in the other direction from the factor to the variable node, and that's going to give some updated information. And as I continually pass this, what I'll find is on a tree, all the messages converge to the exact marginals. That's a good property. And if I'm not on a tree and things are nice, the messages may converge, but maybe not to the exact marginals, but to some approximation of the marginals. In general, when we try and prove things for these algorithms, what we would assume is we take a very large random graph, which is sparse, and so most nodes have these locally tree-like neighborhoods. So if I look at a node, the first, some ball around that node looks like a tree, and in that case, the belief propagation algorithm tends to work well. So that's the case where we most often use it. All right, and so we can just see messages passing back and forth. So in 1962, Gallagher wrote a paper, low density parity check codes. Much later, the term belief propagation was coined by Judea Pearl when he talked about it in a much more general setting. All right, so to try and dig into the belief propagation decoding for a general channel in this kind of talk is a bit silly. But one example where we can really see what goes on is the binary erasure channel. In this case, we can think of the variable nodes, or the circles, as representing a single bit value that's shared by all the factors. And the squares are going to assert that the variables sum to 0 modulo 2. They're this constraint. And so when I want to do iterative decoding on the binary erasure channel, messages are passed in phases. So bits pass messages to checks and checks to bits. And each output message, like we saw in the belief propagation before, it's a key property to mention is this output message only depends on this input message. and it does not depend on the message that came the other way. So there's kind of this leave one out rule that's very important for belief propagation. And so output messages only depend on other input messages, and each message in the binary erasure channel case is either correct or it is an erasure. And so let's see what the message passing rules are for the BEC. So bits pass an erasure if all the other inputs are erased. So why is that true? So I'm using question mark here to denote erasure. Well, I know all these bits have the same value. Every edge attached to a variable node must contain the same value for the correct answer. So if you tell me one of the values, I know all the values. So the only way I'm going to output an erasure is if all the incoming messages are erasures. I can't determine the output. For checks, checks pass the correct value only if all other inputs are correct. So if all of one side is correct, then I know the sum modulo 2 is 0, and I can compute this last guy. Okay? So now, if we look at this guy, if I get even one variable input here, now I know this. But over here, if I have even one erasure, so if I tell you I have a set of vectors summed to 0 modulo 2, but you don't know the value of one, then you really don't know the value of any of them. So this parity function is very hard to predict if you don't know one thing. All right, so these are our message passing rules. And so the way to understand decoding for LDPC codes under belief propagation, in particular on the erasure channel, is to unroll the graph. So the way to think about it is I pick this large random graph, I grab a node, and what I see is that with high probability, each of its neighbors are distinct. Right? So because it's a sparse random graph, and I go down one level and I see again with high probability each of its neighbors are distinct, and they're all distinct here, and so on. And what I find is for any fixed depth, as my block length gets large, I'm going to have this picture with high probability. And so now if I want to analyze what my belief propagation decoder does, it's very easy. What I'm going to do is I'm going to assume that these bottom level of variable nodes were all transmitted through an erasure channel with probability of erasure epsilon. And so they'll all have independently erased with probability epsilon, each one of them. And so I know my message passing rule here. So I have 3 bits going to a check to here. What's the probability this message is an erasure? Well, it's an erasure precisely if any one of those are erasures. And so if I think of y, or let's do x first. If x is the probability of erasure at the input to a check node, then the probability, so if it's degree 3 here, the probability that there are no erasures, or that any one of these are erased, is 1 minus x cubed. And that's what I'm going to get here. And so in that case, because these two parts of the graph are independent, at the next level, again, I'm going to have independent erasures. So the messages coming on these two edges are going to be independent. And now, but they're going to be erased with probability y1 here, 1 minus x1 cubed. And I look at my variable node rule, and my variable node rule says each of the y's comes in. So if I have an erasure of probability y, I also get an observation from the channel. I'm going to know the output to this message if either I have, if any one of these is not erased. So the probability that this is an erasure is that they all have to be erased. I have to get an erasure for each one of these inputs. So that gives me this rule x2, the erasure probability of this message here is going to be epsilon y1 cubed. This is density evolution. This is analyzing what's going on with the message passing for this belief propagation algorithm. Is that a question? All right. And so that's going to tell me. Now we can actually evaluate in this case. Let's assume x1 is 0.6, and we can calculate 0.93. So we see this sequence. What happens is, if you look at the sequence on the x's, x1, x2, 3, it's a decreasing sequence, and so it will converge to a limit. So we can actually work this out and say, analyze the decoder for some fixed number of levels for this very large graph and get an estimate of what the erasure probability is going to be at this bit we're trying to estimate. So Giovanni, did you have a question? Or?
Yeah, sorry, I just wanted to make sure I understand the graph. So basically, the bottom, everything in the bottom is like the code word, the bits of the code word.
So this is kind of a piece of the factor graph. So maybe what I don't have drawn here is like dots right here. So it says, you've picked this giant factor graph. And in fact, it's almost certainly going to have cycles, and it's not going to be a tree. But if you grab a node and just look at a constant depth, as the size goes to infinity, that is almost certainly going to be a tree. So if you
so even if it's not a tree, I guess just so I understand. So the bottom level of nodes are the n bits of the code word.
No, all the yellow nodes are bits of the code word.
Okay.
So all the variable nodes in the coding setup, all the variable nodes are bits of the code word. And so you say like, I want to estimate bit 1. So you grab bit 1, you say, oh, in this particular graph, all the variable nodes have degree 3. Yeah. And so you say, all right, well, let's attach these 3 checks. And there's some other variable nodes. So you're going to do is you're going to try and just observe a small portion, right? If you think of this as an infinite graph, we're just observing a very small portion of it. And we're going to use that to estimate bit 1, for example. And the key that we get from this is we want to know how well is it going to work if I ran it. That's what we're trying to tell with density evolution. All right. So let's see how I'm doing on time. Yeah. I'll probably stop right after this section. So. All right, so the density evolution equations give us an update here. So if I want to know, if I look at the erasure probability from messages from variable nodes to check nodes after L iterations, I have this formula, or this recursion, xl plus 1 is equal to this. And if I plot here the line f of x equal to x, and I compare it to this function here, so that's f of x equal to epsilon 1 minus x cubed squared, there. What I see is that as long as this line, the green line, is below the blue line, if I map these iterations, so if I start at 0.6, so I plug in 0.6, the output is here. These little edges like that is just mapping this this value from the output to the input back here. What I'm going to do is I'm going to walk down this path and see what happens. As long as there's space here, what happens is I'll converge down to 0. So density evolution allows me to write a condition that says, for a very large code, I have some condition that as long as this curve is less than this curve, as I do enough iterations, I'm going to converge down to a 0 erasure probability. And now what we think about is, this is also a function of my erasure probability epsilon, my channel. And so the noise threshold, you can think of this, they call this epsilon BP, is the largest noise parameter for my channel under which this is going to converge to 0. So there's a threshold effect. If epsilon's too large, I would actually get stuck somewhere in the middle, and then this would not happen. All right, and the important part here is that this is easily computed numerically. I just have a one-dimensional recursion. If you do calculate it, what you find is the BP threshold is 0.647. You can use another method. We can calculate the map threshold of this code. We get 0.746. So that means that if we had an optimal decoder, we would do better. And the Shannon threshold, that would be as if I had a capacity achieving code, would be 0.75. Because this code happens to be rate 1/4. All right, so we kind of get the feel for what's going on here. If we want to do some kind of simple low complexity algorithms on our factor graph, we can actually analyze what's going to happen and see what we can handle. It's going to be not as good as the optimal algorithm, and even the optimal algorithm may not achieve the full Shannon theoretical limit because this isn't the best code we could pick. All right. So I think this is a good place to stop for the first hour. It's a good time for questions if people have them.